Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is a video in the course Analytic Methods for Lawyers. Today's video is about good visualizations. What I'm going to show you here is basically how to make great visualizations in the Wolfram language. And let's just get started. So I'm going to show you what I sometimes call the plot zoo. These are the variety, it's only a sample, but a variety of the types of plots that you can make using Wolfram language. Usually there are ways of making similar plots in R using GG graphics, or Python using, I believe, Seaborn or Matplotlib, and you can do similar things in other advanced languages. All right. So you're going to see we've got a lot of different kind of plots we're going to get through. List plots, function plots, heat maps, chloroplaths, geobubble charts, etc. Let's get going. All right, so simplest thing perhaps, or one of the simplest things, is list plot. List plot, here's a bunch of pairs, ordered pairs. We'll evaluate it and we will make a plot of it. All right, so that's how you make a plot of points. What if your dimension has three, what if your data has three values, ordered triples? Then you can put list point plot 3D. And there are our points. What about plots that are based on a list, but that you want to do something else? So here what I'm going to do is called a list line plot. You notice I'm going to sort the plots, and by setting the option mesh to full, you'll see that we get little dots. So watch this. All right, list line plot. If I didn't, there's our points. If I didn't sort them, by the way, it's just a connect the dots kind of thing, and since the original points aren't ordered, it's all over the place. What if I turned off mesh goes to full and said either nothing or let's just take it out? And you can see I'll get a perfectly nice line, but there won't be the little points from which the line was derived. So you can decide whether you want mesh goes to full or not. All right, plots that are implicitly based on tables. All right, so here what we're going to do, all I've done is to create a table of sign values as x goes from 0 to 6 in increments of 0.2. And I've set the option filling goes to axis, which is going to draw little stem lines down. You'll see it. Here we go. All right, so you can see it's plotting each point, and then it's drawing a line down to the axis. And sometimes that sort of cosmetics are very useful. Alternatively, there's a function discrete plot, which sort of builds the table for you. It's saying, look, let x go from 0 to 0.6 in increments of 0.2 and plot sine x. So if we do that, we see a very similar plot. And this is because a feature of discrete plot is this filling goes to the axis is turned on by default. So you don't need to do the filling goes to axis. Function plots. So sometimes we don't want to plot points, we want to plot a function. So the command here is plot, and you put the function or the expression that you want to plot as the first argument and the bounds over which you want it plotted as the second argument. Plot produces two-dimensional plots for univariate functions. There's our friend the logistic sigmoid. We'll see it again. And we've got plot 3D, which produces three-dimensional plots. So here we have a PDF of a distribution, and we want to plot that as x goes from -4 to 4 and as y goes from -4 to 4. So there it is. Or we might want, instead of actually seeing this as a three-dimensional object, we might just want to see the contours on it. And so contour plot has the same structure. The rest of the code is actually completely identical here. And so that is a contour plot of exactly the same object, yes it is, as we created up there. Contour plot, both contour plot and plot 3D have a zillion options that let you control details of this, such as, for example, whether you want the spaces between the contours to be shaded. So you could say something like contour shading. No, that's not what I want. Shading goes to false. And then it's looks like that. But I think it's kind of pretty to leave the shading in. All right. Now, there are some surfaces that, or lines that you can't define by using a simple function. Remember, a function, if I say what's the value of f of x at 3, it needs to be like a number. If it's more than one number, then it's certainly not a conventional function. So to create more complicated objects, you can use parametric plot. And here the idea is I'm going to let t go from 0 to 3 pi over 2. I'm going to let r go from 1 to 2. And I'm going to plot two coordinates. The first is r squared times the square root of t times the cosine of t. And the second is r squared times the sine of t. And so if we do that, we get it is sweeping out this entire area. Okay? So that's parametric plot. I think that's a little bit of a complicated example on mature reflection. Here's a simpler one. We have x as the x-axis, and let's do sine of x plus 3 as the y-axis, and I'll let x go from 0 to 20. Okay, so there's our nice wiggly line. What we could do instead is to have the square root of x times the cosine of x as the x value, and now you can see we start to get a more complicated object of the sort that you can't just do with something like plot. All right, that's parametric plot. Parametric plot has a cousin in 3 dimensions, parametric plot 3D. Here we're setting forth the 3 coordinates. We've got our parameters are u and v, and the x value is cosine of u, the y value is sine of u plus cosine of v, and the z value is sine of v. So we now get I don't know what that is. It's a donut which has kind of skinny parts. It's a very cool shape. I think that's why I picked it. All right, or you can actually have a parametric plot where there's just one parameter, and you'll see that that's going to trace out a locus in 3 dimensions. Well, anybody can do 3 dimensions. How about 4 dimensions? Can we visualize 4 dimensions? And we can, and it starts to get a little tricky, but here's the idea. Let's create a coloring function, and here's our coloring function. It's going to use the colors of the rainbow, and let me see if I can show you how this works. So if I say what is color rainbow of 0.7, it's going to produce, that kind of looks yellow to me. Let's see if 0.01 is red or is that blue? All right, Roy G. Biv, so that's the violet end of the spectrum. 0.99 is the red end of the spectrum. So here what I'm doing is I'm saying it's creating the distance of a point from the point 21. So norm, for example, of 5, let's do this, 5, -3 from 2, 1 is 5, okay? Because the distance between 5 and 2 is 3, and the distance between -3 and 1 is 4, and that gives us our little Pythagorean thing, and so 3 squared plus 4 squared is 25, and the square root of 25 is 5. All right, and we're going to divide that by a denominator, which is the argument here. So radial color produces a function, right? So if I say, what is radial color of 3, it gives us this function. If I say what's radial color of 8, it gives us this function. So I now have a way of coloring the points that's under or coloring whatever that's under my control. All right, so now what we're going to do is we're going to plot our friend the multi-normal distribution. This is the same plot as we made before, the one that's right up here. But instead of having this sort of golden surface, which doesn't give us any additional information about the plot, I'm going to color the function according to the distance of the xy value from the point 2, 1. And I do, for reasons, I need to shut off color function scaling, and you can look up what that option does. All right, so there it is, and we now have colored our plot. So we now have an additional piece of information. We have the x-coordinate, we have the y-coordinate, we have the z-coordinate, but by looking at color, we can get a flavor for how far is the point away from the center. And in fact, if I put this here, let's do this, viewpoint, I'm not so great at this, but above, and view projection, orthographic, all right, so now you can see it a little clearly that you actually are measuring by color the distance between the xy value and the 0.21, at which I believe the PDF is maximized. Yes, it is. All right, let's restore this back to the way we had it originally. And you'll notice that Wolfram is remembering what angle to look at it, which is sometimes great and sometimes annoying. By deleting the cell, we can get it back the way that it was. Well, 4 dimensions is great. What about more? So we can use animation to do more. And so now we are going to animate this function, but the distance is going to have a different denominator, and so I think this is easier to just see. We're going to make a table of 3D plots, and then we're going to animate them. This is going to create a list, right? Table creates a list, and list animate animates a list. So let's see what happens here. Right, so you see as you change the denominator, our distance metric in effect changes, and so the colors of each point changes. So to me it looks sort of like it's melting. Oh, I see. And what I've done also here is I've changed the covariance of the multi-normal distribution. So T has also worked its way into the particulars of the plot. So the details don't need to concern you here. What you should recognize, though, is that through use of list animate, you can animate a table of plots. It doesn't have to be plots this fancy. It could be plots that are a lot simpler. Heat maps are a very popular kind of plot, and the idea is to represent information from some sort of regular grid by coloring the elements of the grid according to their value. So remember our friend the Boston Holmes data. One thing we could do is we could create a matrix that looked at the correlation between all of the data, like the NOx emissions, how is that correlated with crime, and how is freeway access correlated with the racial composition of the area. So if we just look at what this produces, it produces a matrix that is 13 by 13. And if you look at this matrix, it's not, I mean, I think it's hard to really understand that. There just seems to be like a lot of numbers. Humans aren't too good at that. But let's look at if we make a plot. And now we can begin to see that, first of all, you can see that everything is correlated with itself very well. There are things in which I don't know, maybe blue is the opposite of orange, and so there may be things that are anti-correlated. And we have something funny going on with variable 4, which might be worth investigating. All right. We could also do array plot. Array plot is just, it's going to reverse the ordering here. So the first row is going to go to the bottom, and the bottom row is going to go to the top. And by default, it presents information in grayscale. All right, so that's matrix plot and array plot. By the way, starting in recent versions of Wolfram Language, you can have a 3D array plot, which is totally cool. So I'm going to make something called a cellular automaton. I don't want to go through what a cellular automaton is, except to say that this is Stephen Wolfram's earliest claim to fame, was really to develop the idea of a cellular automaton and show that it can actually do interesting computations. Just so you know what this is going to produce, let's plug in, I don't know, rule 30 and have it go for 20 iterations. And it just, what are the dimensions here? It's going to produce a three-dimensional object. So the dimensions are 41 by 41 by 41. All right. So let's create a little manipulate that does an array plot 3D of a cellular automaton where I get to pick the rule and I get to pick the number of iterations that it goes over. And this is telling us, hey, when you see the value 1, color me purple. So there is a picture of a cellular automaton using rule 14. Here's using rule 18. Here's using rule 322. I'm not sure why I picked those, except they do seem to make very cool pictures. That one sort of looks like a Borg cube, doesn't it? Here's for 16 iterations. Here it is running for 21 iterations. Anyway, I could play with this for days. But the point is that for three-dimensional data, you can use array plot 3D to represent that information. Chloropleths. Okay, let's do chloropleths. The idea of a chloropleth is to take some map, usually of some place on Earth, although it doesn't have to be, which has boundaries, and then to color the items within the boundaries according to some function relating to the boundaries. So maybe we might want to color a state according to the level of COVID that exists in it. So we're going to use this resource function here, COVID tracking data. Okay, we're going to stop that right now. Let's go back here. All right, this is going to take a while to download, and so I'm going to shut myself off, and when we come back, we will have the variable COVID assigned to a lot of data that needs to get downloaded from the internet. And I'm not spending time on this code because I don't think you need to understand it, but here we are, we're back. You can see, for example, the population of Arizona is 6.7 million people. Now what we're going to do is we're going to join our population data with our COVID incidence data. Okay, we're going to figure out when was yesterday, and you guys are going to know when I'm making this recording. And now let's just pick the data from yesterday. I'll use a select statement to do this within a query. Again, I'm presenting this not to give you the details of the code, to show you what's possible and to do sort of a non-trivial example of how to make a chloropleth, how to look at something that's actually quite real. So let's evaluate this. Again, this may take a moment. I'm going to cut. Didn't take that long. I'm back. Here's our data set from yesterday. So if, for example, I wanted to, what is this variable called? Recent augmented COVID. Sounds bad. If I wanted to take the data from Arizona, I could say select from the state column and let that be equal to Arizona. Let's check the little box. Let's put a little ampersand there to make that a function. Let's close and recent augmented COVID. And so here's what we know about COVID. We know that yesterday um, there were 3,060 people hospitalized. I think that's down from the peak. I remember, yeah, there was a big problem in Arizona a while back. Actually, we have 56 total pieces of data here, all sorts of things. And at the end, though, I have my population. That's what I wanted to show you. All right, so now I think I hope we're ready to make our chloropleth. So the command in Wolfram Language to make a chloropleth is not something chloropleth, it's georegion value plot, which does explain really generically what's going on. And we're going to take our recent augmented COVID, we're going to plot that data. You notice the use of a pure function here. We're going to let our range be the United States. We're going to color the states according to the temperature map, not have any legends. And what are we going to use as our data? We're going to use the number that are hospitalized currently divided by the population. So this is some measure of the strain on the hospital system that currently exists in the United States, although it doesn't take into account the pre-existing strength of the hospital system. But all of this is to show you georegion value plot in a way that I hope is interesting. And here we are. So what can we see? We can see that Arizona is still actually having a bad time of it. We can see Georgia, we can see New York, not so good, Texas, not so good, and then these northern states up here at the moment seem to be doing pretty well with COVID. You know, it's interesting, earlier North Dakota was in bad shape. All right, that's a chloropleth. A geobubble chart. So the idea of a geobubble chart is to put bubbles over geographic entities that are scaled to some fact about the geographic entity. So here is the population of various South American countries. Let's make a geobubble chart and see. Okay, so there's big Brazil, there's little Uruguay, Colombia, Venezuela, etc. All right, so that's a geobubble chart. We can also do it for data on earthquakes. So let's get the earthquakes around Mexico City, and actually let's do it through right now. So let's have it bring that in. And this need not worry you as to what this is all about. And now let's make a geobubble chart of earthquakes in Mexico City. I'm having to get certain data from, like, what does the terrain look like from the Digital Globe Geo server. Again, really, I just want to show you a cool geobubble chart. Data. And voila. All right, so we see that there were some significant earthquakes, looks like back in November of 2019, and it looks like there was an offshore quake here. So what I'm doing here is I'm associating a bubble with the geographic location of the quake. This seems to be some pretty bad fault here. And the size of the bubble is reflecting the size of the quake. All right, geobubble charts in the book. Now let's talk about faceting. Most good graphics programs have faceting. R and its ggplot package is, I think, sort of famous for faceting. And we can do faceted graphics in Wolfram Language too. And I think it's easier just to see it than to try to explain it. All right, to do faceting, we're going to download a famous data set called the Fisher Iris data set. And here's what it has in it. It's got various characteristics associated with flowers, and then it tells you, ooh, this flower is a setosa. And this flower is a versicolor type of iris. These are, I don't know, subspecies or species of irises. Every computer science student needs to know about irises. All right, so there's our iris data. And iris form is going to tell us what these various numbers mean. And so it's the sepal length in centimeters, the sepal width in centimeters, and it might be sepal, I really don't know, petal length, etc. So that's what we want. I'm going to associate colors with the different species of irises. Setosas are blue, virginicas are purple, and versicolors are whatever that color is. Tan? Bronze? I don't know. All right, now what we're going to do is we are going to, I'm going to try something out on you here. Let's do this. I have a query, and I haven't taught you about queries, and I may never teach you about queries. But queries is basically a way of generating code. And so what we're going to do is we're going to take our data. We're going to group the data based on its species. That was the last item. And then only report out the first item, which is the actual data on the dimension. So we're going to group by this last thing here, and then we're just going to keep the actual data on the irises. Then what we're going to do is we're only going to take certain slices of the data, and then what we're going to do is we're going to make a list plot labeling our axes according to which of these we have grabbed, and then the rest of this is just cosmetics code, including what colors we're going to use to represent the points. So that's what's going on with query. I would recognize that it's a bit obscure if you haven't encountered it first. All right, but let's actually just do it. All right, and so now what you see is here is the sepal length versus sepal width for Setosa irises. Here is the length versus width for versicolor irises, and here is the length versus width for virginica irises. And so I have faceted length versus width into three categories depending on the species. And so that is faceted graphics in Wolfram Language, and the command that sort of anchors this is this grouping command. Cartograms. All right, what's a cartogram? Cartograms are where you try to retain information either about the shape or the position of an object, but make its size depend on some value. And so there is no currently built-in cartogram function in Wolfram Language, but there is a resource function called a Dorling cartogram, and I'm just going to show you what this is. My hope is, so here what we've done is to color and size the states of the United States based on their population. So this is a type of cartogram. We can also do it based on what we saw earlier about the hospitalization rate, and you can see that Arizona is now considerably bigger than it might have been otherwise. There are fancier cartograms than the Dorling cartogram. Here's one in which someone has, this was not done in Wolfram Language, has shown the size of the nations based on their population. And so we can see India has gotten really, really big. Greenland appears to have sadly dropped off the map. Russia, interestingly enough, has really shrunk. It's a giant country, but China has effectively taken it over. The Koreas are big. Anyway, that is a cartogram, and it's often a useful way of visualizing information. If this were a real zoo trip, you might want to go sit on a bench and relax for a few minutes, but since it's only a metaphorical zoo, we will proceed onwards. Let's talk about time series. So here what we're going to do is get data in which the x-axis is time, and here we're going to look at the share price of NVIDIA. It's getting data from the Wolfram server, and here you can see that NVIDIA had quite a run-up during the Bitcoin boom, and interestingly, NVIDIA is way up again. Remind me to invest. And we might have a little fun looking at this little sort of silly stock GameStop. By the way, that is Apple L that lets you copy down the last output. And GameStop is NYSE GME. And let's see what's happened to this boring little stock games. And yeah, you can see it was kind of, and in fact, we really need to put plot range all because my belief is it's gone off the charts here. Yeah, so you can see this crazy spike as a result of the Reddit furor and all the rest. Timelines. So, very useful thing I like to produce are timelines. And what we're going to do is, here what you're going to do is you're going to put in the times or the intervals that you're interested in. So here's a timeline plot. And here what we're going to do is look at how the presidential election basically works. So here what I've done is also to label some of these dates with a tooltip. You'll see how that works. All right, so let's run this code. And now you can see a visualization of the presidential election of 2020. And also, just so you know what tooltips are, if you hover over the item, it will give you some additional information. Here's the source of when something called the Safe Harbor Day was. Here's how you know when the congressional terms expire, etc. So these are timeline plots, and they're very useful for people doing things that relate to history. Charts. All right, lots of different kinds of charts. What's the difference between a chart and a graphic? Charts are kind of special purpose, and they often sort of come packaged with a higher level of decoration. All right, presumably you've all seen pie charts in your life. There's a pie chart. So this is the size of the slices, and you see that represented here. Or you can use an association, in which case you can get labels, and now you know that this C slice here, the big slice, is slice C. If you want to show the values that are associated with each pie slice, here's a little piece of code that I think is pretty nice. All right, just like pie charts, there are bar charts. You've probably all seen bar charts. If you want to have multiple data sets, you can do it this way. I'm not a huge fan of these kinds of bar charts, but there you are. You can change the way that the information is laid out. Here it's all separated. See, the yuks have these 4 bars and the zooks have these 4 bars separated horizontally. If I say stacked, I get what is arguably, depends on what you're trying to show, a nicer presentation in which we have the yuks, and you can see that D is somewhat dominant among the yuks, but C is kind of close behind, and we can see the zooks have more in total, and D is really this gigantic thing, and C is not as big. All right, so we can use, bar chart and histogram are very closely related. Bar chart is used when the data's already been counted and binned, and histogram is when you haven't done any counting or binning, you just have the data itself. So here I'm producing 1,000 random numbers from a normal distribution, and there's our histogram. There are paired bar charts. Let me just show you how this works. All right, so here's our paired bar chart, and the idea here is that we have the age distribution. I'm not sure if this is going to be males or females, and in fact, that's why it's useful to decorate these things. Here's females, and here are males, and so sadly you can see that as we get up the age pyramid, there are a lot more women than men. But we're doing really well at age 20. All right, that is paired bar charts, bubble charts. So let's show those. What you're going to try and do, the idea here is you have three-dimensional information, but you only want to represent it in 2 dimensions. So 2 of the dimensions are used to place the bubble, and 1 dimension is used to size the bubble. So here's our bubble data, and we're going to use these first 2 points to place it, and the third point to have the size of the bubble. Oh, that's just our bubble data. Now let's bubble chart our bubble data. All right, and so you can see different size bubbles. You can have multiple data sets for bubbles. So let's augment our original bubble data with a new set of bubble data, and it tells you that by coloring the points differently, bubbles differently, depending on which data set it came from. Box and whisker charts. You may have done these in school at some point. It's an old-fashioned way of basically comparing distributions. And the idea is you have some central area, it's usually colored, that covers most of the distribution. You might have some markers that show distributional landmarks, like the mean or the median. And then you might designate the outliers in some fashion. So here what we're going to do is we are going to get data on university salaries at some university, and we are then going to group the data according to whether the professor is in one of these 7 fields. So don't worry about this code, but now you can see here's the salaries in the math department, the history department, it's a well-paying school, English department. All right, and now we're going to make a box whisker chart of that grouped data. We'll have it do some labeling, and there's our box and whisker chart. So this is the box, and these are the whiskers. And I've labeled the data. This little bar here, I believe, represents the median. This is something that you can produce relatively easily with Wolfram Language. There's a more modern version, I would say, of these box and whisker charts, which you can't really do by hand, which is why they didn't teach it to you in school, called a distribution chart. It's sometimes called a violin plot. Let's just make a violin plot of the data. So it's the same data, and you see how this kind of looks like a violin, showing the spread. So in math, the thickness here is basically representing in some sense the PDF of the distribution at that value. So you see, for whatever reason, law professors are strung out. You can also see a flaw of the distribution chart implementation here, in that it is extrapolating that there might be law professors that have negative salaries, and I can assure you that no self-respecting law professor would have a negative salary. All right, you can also color code your distribution charts, and here I recognized that my original notebook had some beautiful code in it that has nothing to do with distribution charts. I don't know why it was in there. And so what I've now done is to move it down to an optional section at the end, and you can take a look at it if you choose to do so. All right. We could also talk about animated bubble charts and horse race plots. So let's do that. Here, Wolfram Language does not yet have this. If you go, though, to these websites, you will see how they can be created. Here's how you can do it in Python. And you can run Python from within Wolfram Language, but I'm not going to teach you that here. All right, so let's just for fun, maybe. No, you know what? I'm going to let you do this on your own. You can look at an animated bubble chart or an animated horse race plot on your own. Let's go look at multi-axis plots. So the idea here is to deal with the problem of displaying information that has more than 3 dimensions. There are a couple of techniques that have evolved recently. One is called a radar plot or a spider plot, or Wolfram Language calls it a radial axis plot. And so again, let's take our Fisher iris data, and what we're going to get here is just a short form of the variable labels. Let's get that data in again. What we're going to do is now group the data by the species, keep the features data, and then use our friend ArrayReduce to compute the mean of each feature for each species. So you can see these are the mean values for, I don't know what this is. This is the sepal length, sepal width, petal length, and petal width of the Setosa iris. So we've got 4 pieces of data on each of these, and we might like to try to compare them. So we're going to use a radial axis plot to do this. And you can see that we're now able to describe the 4 dimensions of the Setosa iris using this quadrilateral here. It looks like a triangle, but it's actually bent, but evidently the Setosa iris has a very narrow petal. Who knew? And so that actually might be a way of figuring out which irises were Setosas. But you can now are able to compare, for example, you can see that the petal length of the Virginica iris on average is considerably bigger than the petal length of the Setosa iris. Again, perhaps giving us a basis for telling our irises apart. You can also use a parallel axis plot, and here the idea is we're going to, like the first axis here is the sepal length, so you can see that for Virginicas have the biggest sepal length, but the Setosa is fat and it has a high sepal width. And again, the Virginicas have this high petal length and petal width. So that is a parallel axis plot. It's used for representing high dimensional data. This concludes what I would describe as the mandatory component of this video. And what I hope I've shown you is the variety of ways in which you can use graphics to present information. There are other libraries and other languages that perform many of these visualizations and more in a different, sometimes better way. But what I hope I've shown you is that Wolfram Language has immense flexibility in displaying a variety of graphics. There are many, many forms of graphics I haven't shown you, but that would make the video even longer. But this gives you an idea as to what can be done. For those who want to see these sort of graphics in action, I'm going to make a bonus video that's going to show how to tell a story with visualizations. The topic's going to be tort law, and it's going to take off from the Learned Hand Standard. But I think putting it in this video, even though it's optional, is just going to make the video too long. It's a rather involved story, one that I would urge you to watch if and when you have time. For now, though, that's our look at good visualizations.